In the coming decades, the primary driver of disaster-related losses will not merely be the frequency of hazards, but the exponential growth of populations and assets in high-risk, poorly planned urban areas. Consequently, urban resilience has evolved beyond the narrow confines of disaster risk mitigation. It is now a fundamental paradigm for sustainable urbanization. This shift necessitates integrating hazard management into the DNA of everyday urban development, from land use zoning and municipal budgeting to the provision of basic services in informal settlements. The complexity of modern cities, characterized by dense interdependencies between energy, water, and transport systems, means that a failure in one sector can trigger catastrophic cascading effects. An urban resilience assessment serves as the vital diagnostic tool to navigate this complexity. It bridges the conceptual gap between high-level policy goals and ground-level execution by providing the evidence-based data needed to quantify the potential returns on resilience investments. The economic imperative is clear. Every dollar invested in resilience can save up to $4 in future emergency response and reconstruction costs. However, achieving this requires moving away from static planning. Modern urbanization must account for deep uncertainty, the reality that climate change and rapid migration patterns are non-linear and unpredictable. Resilience planning, therefore, is not about predicting a single future but about building the capacity to remain functional across a range of possible futures. Without these metrics, resilience remains a fuzzy or purely rhetorical concept. However, by utilizing frameworks which incorporates localized social vulnerability data, the URA becomes a rigorous roadmap. It empowers decision-makers to move from reactive crisis management to proactive, forward-looking, infrastructure design. By accounting for long-term climate uncertainties and socio-economic shifts, EURA ensures that multi-billion-dollar investments in the built environment are not only robust today but remain functional and adaptive for a 50-year horizon or more. This presentation outlines a comprehensive roadmap for transitioning from theoretical resilience concepts to an operational urban resilience assessment framework. It begins by establishing clear learning objectives that prioritize a safe-to-fail engineering philosophy and the operationalization of the full disaster lifecycle. The narrative then explores the multidimensional perspectives of resilience, detailing the 5 critical pillars: social, economic, institutional, infrastructure, and environmental, and their specific strategic indicators. Central to the discussion are the core frameworks, such as WRI's Urban Community Resilience Assessment and the World Bank's Risk-Based Investment Principles, which provide the evidence-based metrics necessary to bridge the conceptual gap in urban policy. The presentation further delves into resilient urban design principles, emphasizing how modularity and redundancy act as systemic safety valves against cascading failures. By addressing temporal dynamics and the management of deep uncertainties, the session guides practitioners through the implementation phase, focusing on mainstreaming resilience into municipal budgeting and participatory governance. Finally, it concludes with strategic takeaways that highlight the necessity of open-source risk data and the integration of ecosystem-based solutions to ensure long-term, equitable urban sustainability. Upon completing this toolkit, readers will be able to define urban resilience as the ability of a system to resist, absorb, accommodate, and recover from impacts in a timely and efficient manner. Evaluate URA frameworks, transitioning from top-down aggregate exposure data to granular, building-specific, and community-level assessments. Analyze the 5 dimensions of resilience, with an added focus on how social vulnerability and ecosystem management intersect with infrastructure. Integrate design principles like modularity and safe-to-fail natural infrastructure into urban master planning. Operationalize temporal dynamics, ensuring resilience strategies address all stages of the disaster cycle: plan, absorb, recover, and adapt. Urban resilience is a complex adaptive system property. To assess a city effectively, one must move beyond top-down infrastructure audits and adopt a holistic perspective. A comprehensive urban resilience assessment must track indicators across these 5 essential pillars: social resilience, the human inequity factor. The urban poor are disproportionately affected by climate events due to existing social vulnerabilities and political exclusion. Social resilience assesses the social software of the city, its human capital and equity. It focuses on the ability of individuals and neighborhoods to organize and act during a crisis. This dimension recognizes that social cohesion, the level of trust and mutual aid within a neighborhood, is often a more effective predictor of survival during a disaster than the strength of a building. Key indicators: literacy rates, social capital, trust and neighborhood networks, access to emergency information, and the presence of locally respected community organizations. Expanded metrics. Asterisk access to basic services. Percentage of households with reliable access to safe drinking water, sanitation, and waste collection during and after shocks. Information equity. Proportion of the population with access to early warning systems via mobile technology or community megaphones, urban community resilience assessment, individual level data. Vulnerable group density. Mapping of concentrations of the elderly, female-headed households, and non-native speakers relative to hazard zones. Community preparedness habits. Number of households with localized resilience kits, and familiarity with neighborhood evacuation routes. Economic resilience, diversification and financial buffers. A resilient city avoids the fragility of single-sector dependency. Economic resilience involves the ability of a city to maintain its economic functions despite shocks. This requires a diverse local economy and the financial capacity of residents to recover. If a city relies solely on tourism or a single manufacturing plant, a disaster in that sector causes a total systemic collapse. Economic resilience also involves the speed at which local markets can reopen and supply chains can be rerouted. Key indicators: livelihood diversity, Gini coefficient, income equality, household financial reserves, and the availability of microinsurance or climate risk financial products. Expanded metrics. Livelihood mobility. Percentage of workers with transferable skills that allow for rapid re-employment post-disaster. SME robustness. Availability of emergency credit lines and business continuity grants for small and medium enterprises. Remittance reliability. Resilience of digital payment systems to ensure the continued flow of financial aid from outside the affected area. Market recovery speed. Estimated time for local food and supply markets to resume operations following a 1 in 50-year hazard. Institutional resilience, governance and policy synergy. This pillar concerns the enabling environment created by local governments. Institutional resilience is identified as a primary driver for the other 4 pillars. It evaluates the transparency of governance and the integration of disaster risk management into long-term urban planning. It asks, does the city have the legal authority and the budgetary flexibility to redirect funds during a crisis? Institutional resilience is built through polycentric governance, where power is shared across multiple scales, from neighborhood councils to national ministries. Key indicators: degree of policy mainstreaming, interagency coordination, transparency in disaster fund allocation, and public-private community partnerships. Expanded metrics. Budgetary contingency. Percentage of municipal budget held in quick release contingency funds for immediate disaster response. Legislative integration. Presence of mandatory resilience audits for all new large-scale infrastructure projects. Polycentric density. Number of active, legally recognized neighborhood-level resilience councils with a direct line to City Hall. Data interoperability. Existence of shared risk platforms where police, fire, health, and planning departments can view real-time, synchronized hazard data, e.g., EPD-Net outputs. Infrastructure and physical resilience, robustness and upgrading. Infrastructure resilience is not merely about fail-safe building codes. There is a need to highlight the importance of urban upgrading, improving basic services and housing in informal settlements. It also involves the redundancy of critical lifelines, power, water, and transport. For example, a resilient energy system might use microgrids that can operate independently if the main grid fails. This pillar also includes protective infrastructure, such as seawalls, but emphasizes that these should be used in conjunction with soft solutions. Key indicators: seismic, flood compliance of structures, redundant energy grids, land acquisition plans for safe resettlement, and the availability of open-source risk data, e.g., EPD-Net. Expanded metrics. Critical asset redundancy. Number of alternative routes for emergency vehicles per district and N+1 redundancy for power substations. Urban upgrading coverage. Percentage of informal settlements that have undergone structural retrofitting or drainage improvements. Service continuity horizons. Rated capacity of hospitals and shelters to operate autonomously off-grid for at least 72 hours. Safe land availability. identified acreage of low-risk land reserved for temporary housing or permanent resettlement. Environmental resilience. Ecosystem-based solutions. Often neglected, the critical fifth dimension recognizes the city as an ecosystem. Natural infrastructure can buffer shocks more cost-effectively than gray infrastructure. Environmental resilience assesses the health of the natural assets that protect the city. Mangroves, wetlands, and urban forests are not just amenities on a systemic level, they provide essential services like flood absorption and heat regulation. Key indicators. Quality of ecosystem services, wetlands for flood control, greenbelts for heat mitigation, resource efficiency, water, waste management, and post-disturbance environmental health metrics. Expanded metrics. Flood absorption capacity. Percentage of urban land composed of permeable surfaces or green sponges, parks, wetlands. Natural buffer integrity. Area of mangroves or coastal dunes maintained as strictly non-developmental protection zones. Urban heat index. Temperature differential between high-density concrete areas and vegetated, cool islands. Resource circularity. Percentage of municipal waste and wastewater treated and reused locally, reducing dependency on external supply chains during crises. The operationalization of resilience requires frameworks that transform qualitative concepts into quantitative indices. Urban Community Resilience Assessment, UCRA, introduced by WRI. This tool uses a 3-level scorecard, city, community, and individual, to integrate neighborhood-level data into urban planning. It specifically targets the data gap in informal settlements where official statistics often fail to capture the true level of vulnerability. INA SAFE, Indonesia Scenario Assessment for Emergencies, an open-source risk assessment tool used to produce realistic natural disaster loss scenarios for better planning. It allows non-experts to visualize the impact of a 1 in 100-year flood on specific schools, hospitals, and roads. Baseline Resilience Indicators for Communities, BRIC, utilizes sub-indices across the 5 dimensions to identify spatial variations, essential for identifying which urban districts are falling behind. It allows for a relative ranking of resilience, helping states allocate resources to the most fragile counties or districts. Disaster Resilience Index, DRI, a self-assessment tool used by major cities like Istanbul to monitor how risk reduction is mainstreamed into day-to-day city development. It focuses heavily on the progress of institutional mandates and legislative compliance. Urban Disaster Risk Index, UDRI, adopts a holistic approach by combining physical risk with social fragility. It quantifies the city's capacity to cope through indicators like healthcare access and insurance mechanisms. It is particularly useful for identifying the aggravated risk, where high hazard exposure meets low social coping capacity. A robust urban resilience assessment serves as more than a diagnostic report. It functions as a strategic design guide for transitioning from fail-safe engineering, which assumes absolute protection, to safe-to-fail systems. This approach acknowledges that while disturbances are inevitable, their consequences can be managed through intelligent design. Diversity and redundancy. Resilient cities must move beyond single-sector dependency. This involves establishing redundant pathways for critical flows such as energy, water, and transport. Redundancy ensures that if one substation or arterial road is compromised, alternative nodes can absorb the load, preventing a total system shutdown. Diversity in this context also means having a mix of centralized and decentralized systems, e.g., combining large power plants with rooftop solar. Connectivity and modularity. While connectivity facilitates the efficient flow of resources and information, it can also accelerate the cascading effect of a disaster. Modularity is emphasized as a critical safety valve. By designing urban districts as semi-independent modules, planners can isolate failures, e.g., a localized flood or grid failure, ensuring the disturbance does not paralyze the entire metropolitan system. It is the difference between a string of Christmas lights where one bulb takes out the whole strand, and a modular system where each light operates independently. Adaptive design and flexibility. Infrastructure must be designed for a 20 to 50-year horizon, accounting for nonlinear climate shifts. This includes adopting nature-based solutions, such as permeable pavements and sponge city, green belts, that provide flexible buffers compared to rigid, gray infrastructure. Adaptive design also means creating multifunctional spaces For instance, a public park that doubles as a flood detention basin during extreme rainfall. Social learning and inclusive agency. Physical design is insufficient without social software. Resilient design integrates social learning by transforming public spaces into hubs for emergency training and community engagement. By fostering resilience habits and providing localized response kits, cities ensure that residents are not passive victims but active agents capable of navigating crises through communal practices and decentralized governance. These principles transform the URA from a static assessment into a dynamic roadmap, ensuring that every infrastructure investment contributes to a city's long-term capacity to plan, absorb, recover, and adapt. Assessments must move beyond static snapshots to address long-term uncertainty. Temporal cycles. Planning must account for different time horizons, from annual budgets to 50-year infrastructure designs. Resilience is not a destination but a cycle. The plan phase involves zoning and risk assessment. Absorb is the structural integrity during the event. Recover is the speed of service restoration. And adapt is the post-event learning that informs the next plan phase. Cross-scale interactions. Assessments should be disaggregated by factors such as sex, age, and employment status to reveal granular insights into community resilience. A city may appear resilient at the aggregate level while masking extreme vulnerability in a single neighborhood. URA must look down at the household level and up at the national policy level simultaneously. Methodological transparency. Using sustainable risk information systems that allow for systemic communication of risk to all stakeholders. This involves open data, policies where risk maps are public, allowing citizens to make informed decisions about where to live and how to invest. The final stage involves mainstreaming resilience into the project cycle. Urban upgrading, prioritizing projects that provide safe environmental conditions through improved housing for the most vulnerable. This is the most direct way to reduce the base-level risk in rapidly growing cities. Risk-based land use planning. Using GIS tools to identify the safest areas for future development. It involves the difficult political work of preventing development in high-risk zones, such as floodplains or steep slopes, and providing viable alternatives for low-income residents. Participatory governance. Engaging residents in the identification and implementation of climate resilience measures on the ground. When communities co-design a drainage system, they are more likely to maintain it, ensuring long-term project sustainability. Takeaway 1. Effective strategies must reflect the specific needs of vulnerable communities and include them in planning processes to ensure social equity. The cases reveal that climate impacts are distributed unevenly, therefore, top-down policies often fail to reach those most at risk. Social equity is not merely a moral goal but a functional necessity for resilience. If the urban poor, who often reside in high-risk informal settlements, are excluded from planning, the city's overall risk profile remains high. Planners must transition from planning for the people to planning with the people. This involves utilizing the UCRA methodology to capture the lived experience of residents, ensuring that interventions address specific barriers such as lack of tenure, limited access to information, and inadequate representation in municipal governance. Takeaway 2. Investing in open-source risk data and analytical tools like INASAFE is critical for a systemic, evidence-based understanding of risk. Cities cannot manage what they cannot measure. High-quality risk data must be treated as a public good. Open-source tools like INASAFE democratize risk information, allowing local stakeholders to run their own impact scenarios. This transparency ensures that risk assessments are not locked in academic silos but are used to inform real-world decisions, from hospital placement to emergency evacuation routes. A systemic understanding requires a sustainable risk information system, where data is constantly updated, reflecting the dynamic nature of urban growth and changing hazard patterns. Takeaway 3. Ecosystem-based approaches, environmental resilience, can significantly decrease infrastructure costs while building long-term natural capacity. The environmental dimension is the most neglected pillar, yet it offers the most sustainable, safe-to-fail solutions. Instead of relying solely on expensive, gray infrastructure like concrete seawalls, cities should invest in blue-green infrastructure. Wetlands, mangroves, and urban forests provide co-benefits. They absorb floodwaters and reduce heat islands while simultaneously enhancing biodiversity and property values. Integrating ecosystem management into urban design decreases the long-term maintenance costs associated with traditional engineering and provides a flexible buffer that can adapt to rising sea levels more naturally than rigid structures. Takeaway 4. Resilience is not a one-time project or a checkbox. It must be part of everyday urban development to ensure cities can plan, absorb, recover, and adapt. Resilience is an ongoing process of mainstreaming. It must be embedded into the project cycle, municipal budgeting, and land use law. A city's resilience is tested every day, not just during disasters. By treating resilience as a new urban paradigm, cities move away from reactive, disaster management, toward proactive, resilient development. This temporal perspective ensures that the city is constantly learning. The adapt phase of one event must directly inform the plan phase of the next, creating a virtuous cycle of continuous improvement. Takeaway 5. By analyzing 5 pillars through both top-down and bottom-up lenses, planners can identify resilience gaps, such as a neighborhood that is physically robust but socially isolated, and prioritize investments that provide the highest systemic return. A multi-scalar approach is essential to avoid false resilience. Aggregate data can mask localized vulnerabilities. A neighborhood might have modern building codes, infrastructure, and a strong local economic, but if residents do not trust their local government, institutional, or lack social networks, they may still fail to recover post-shock. Identifying these resilience gaps allows for strategic prioritization. Instead of broad, inefficient spending, planners can target investments, such as building a community center in an isolated but physically safe district, to maximize the systemic resilience dividend.